today we're going to look at error chances when we make some type of a decision about a hypothesis test. And we have actually two types of error that we can make when we have a hypothesis test. And remember, we're assuming that a certain null is true, and then we find some sample, and we get an X bar, and then we're trying to find what kind of evidence we have as to whether our sample looks like it is consistent with the mean that we're assuming, or whether we have evidence to reject the null and say that the null is actually wrong and that the alternative is true. So anytime we make a decision, we have a chance of being wrong. And so let's look at our little table here. And let's say that the null hypothesis is actually true. Well, if the null hypothesis is true, and we collect data that seems to be consistent, so we say we don't have any evidence against it, and we, in no better terms, say that we accept the null, or we say that we have no evidence against it, so we think that the null is correct, and the null is actually correct, then we've made the correct decision. However, what happens if we have a scenario in which we're assuming, again, that the null is a certain value? However, we get evidence that, say, is kind of unusual. We get an oddball number, and we find what the likelihood of that value is. We find the p-value that corresponds with this x bar we get. And so even though the mean is actually what we're assuming to be true, we just get one of these weird numbers, a particularly low value or a particularly high value, and that would cause us to say we have evidence against the null, and we would reject it. Well, in that case, we would be making a bad decision. The null is true, but we're finding something that is unusual, inconsistent with that mean, and then we are rejecting it. That's called a type 1 error. So if we reject the null when the null was actually a true statement, then we have a type 1 error. Now, on the other hand, if we have the null that we're assuming to be true is actually wrong, meaning that the alternative mean is actually something that's true. So we're assuming the mean is a certain value, and we collect an X bar, and let's say we get an X bar that, again, is one of those odd ducks, one of those values that causes us to have a small p-value. And so we say, we have evidence against the null, and so we reject it, and we say the alternative is true. Well, if the alternative is true, we've made a good choice. We've made a good decision. On the other hand, even if this mean is not correct, sometimes we will get a value that will say we don't have evidence against the null, and we think that our X bar is consistent with the mean being the value that we're assuming to be true, when in fact this mean is actually not right. So if we find evidence that's consistent with the null hypothesis, causing us to accept it or not find evidence against it, however, the mean really was wrong, the null was actually wrong, that the alternative was true, that's when we have what we call a type 2 error. Now, let's look at an example, and we'll talk about the calculations of the type 2 error. That's going to be much more difficult to find than a type 1 error. We'll find that the type 1 error is actually very, very easy to find. So, let's look at our example. So from past years of data, it's been found that the mean ACT score, national score, was 18.6 in this year with a standard deviation of 3.4. And we have Jamie, who wants to find if students at wannabe high school have scores that are statistically significantly higher than the national average. So she's going to take a simple random sample from that school of size 40, and we want to find out what is the chance that she's going to have a type 1 error, what is the chance she's going to have a type 2 error. So first of all, she would be assuming that wannabe high school has a mean that's no different from the national average, and alternatively, that the mean is higher than the national average. Now, what would it mean to have a type 1 error? A type 1 error, remember, takes place if the actual null is true, however, you get some sample that causes you to reject it. So a type 1 error would be that we find evidence with an X bar that would tell us that the null is not true, causing us to reject it. However, the null was actually true. So it would be if she sampled 40 people from wannabe high school who actually have a pretty high ACT score compared to this, and we go, ooh, the wannabe high school actually scores higher, when in fact they actually, if we did a census, would have a mean of 18.6. Now, the likelihood of that happening is actually just our significance level. Because if the mean is really 18.6, and if we sample 40 numbers, remember, and if it's truly at wannabe high school is 18.6, sometimes we will get numbers that are significantly higher and significantly lower, but we're only testing the graded end tail at this point. And so if we're going to use a significance level of 5%, that means that once an X bar gets in this region, that would cause us to reject the null, and we know that that will happen. In fact, it would happen, whatever our significance level is, that's how often it would happen if the true mean is 18.6. Now, what does it mean to have a type 2 error? A type 2 error is where we don't find evidence against the null. So we find something that is consistent with the mean that we're assuming to be true. And that causes us to, quote, accept the null. However, the null actually was not true. So we find something that seems to be consistent. It's not in what we will call our rejection zone. And so we say, well, we don't think we have evidence against the null. We'll say the null, it's right. When in reality, the null is actually not correct. Some alternative where it's actually higher than 18.6 is true. Let's turn our page. Now, we can't actually find the probability of just type 2 error in general. We have to find the likelihood of a type 2 error against a particular alternative, because as the alternative, which is just greater than 18.6, if the alternative mean is just a little bit higher than 18.6, that's a different story than if it's a lot higher than 18.6. So you'll see what I mean as we go on. So we want to find what is the likelihood of having a type 2 error if this wannabe high school actually has a mean of 20.2 on the ACT. So remember what a probability of a type 2 error is. The probability of a type 2 error is where we accept the null when really we shouldn't be accepting the null, that the alternative is true. And in fact, the alternative is this specific alternative value. We always have to find it against a specific alternative, and the specific mean alternative that we're going to find is this 20.2. Now, it's kind of a two-step process, and the first thing we have to do is find out when would we reject, when would we accept the null with the hypotheses that we're starting out with. And so remember, we're using the null hypothesis of the mean is 18.6. That's what we're assuming wannabe high school has as its mean. And alternately, we think it's higher than 18.6. So we first of all have to find when would we reject the null, when would we accept the null. And so we're assuming 18.6 here is in the center. And we know that there comes a point when an X bar gets high enough, it ends up causing us to reject the null. Alternately, we either say we don't reject the null down here, or some texts will say accept. But we have to be careful about saying just accept. We're not rejecting, really, when we're here. So we have to find this score. And the first thing I do is I find the z-score that corresponds with this upper tail of 5%, which is my significance level. And so I look this up in the back part of the book, or we can look it up in the front part of the book as well. But notice that this is a positive z-value when we're up here. And then I need to transform that into an X bar. And so we could use this idea that a z-score is equal to my number, the X bar I get, minus what I'm assuming to be true, divided by the standard deviation over the square root of n. And so I'm transforming that number. I know the z-score is that 1.645. I know that I'm trying to find what this X bar is. I'm assuming the mean to be 18.6, and I've got that standard deviation over the square root of my sample size right here. And so I multiplied both sides by this value and added on the 18.6, and that's where I came up with this calculation. Okay, so multiplying these and adding that together, I got the 19.48. So the z-value on the normal distribution is 1.645, and the x-bar that that corresponds with is this 19.48. So we have to find where would we accept the null and where would we basically reject the null. And we would accept the null and say, hey, that's just normal variability. Anytime we get an x-bar that is less than or equal to this 19.48. So if we sampled 40 numbers, or if Jamie sampled 40 numbers, if she got an x-bar that was 19.48 or less, that would be evidence to say, that's just normal variability. As opposed to if she got something that was greater than 19.48, we'd say, ooh, that's unusual if the mean is 18.6, and that would cause us to reject the null if she got an x bar that was up here. Okay, so again, we want to think, what are we finding? We're finding the probability that she accepts the null when an alternative value is true. This is when she'll accept the null. So our second thing is to find the likelihood of accepting the null, this region, if some alternative mean is true. So now we have to use that alternative mean. So I'm going to draw my picture. So this is what we're saying, assumingly that wannabe high school is actually this. So the likelihood of a type 2 error is what's the probability that we accept the null when a particular alternative hypothesis is actually true. So here was our original picture. We find our acceptance zone, what would cause us to accept the null, and then we find the likelihood of that in our other picture. And so I need to find, and I took the 19.48 and plopped that zone. That's my acceptance zone, which I sometimes just call an AZ, my acceptance zone. And I find the likelihood of that by taking the number minus the mean that now is in my new picture, divided by the standard deviation, which is staying the same. And I find my z-value and my corresponding probability. So I have a 9% chance of making a type 2 error, that is, of accepting the null, when the mean is actually changed to 20.2. So if Wannabe's high school is really 20.2, 9% of the time I'm going to make a mistake and say, oh no, that's just normal variability when I sample 40 numbers. And I'm going to say that my mean is not different from 18.6, that it's just the same, when in fact it's actually higher than 18.6. It's all the way up to 20.2. Now the further that this number is away from what we're assuming, the less likely we are to have an error. And we will do some examples, more examples to see that type of thing in class. Now the next concept is called power. And the power is the probability that a significance test will reject the null when a particular alternative value of the parameter is true. Now let's stop a second. That means that you will reject the null when the null is wrong. That's good. You want to reject the null when the alternative is true. So the power is something you actually want high. You want a lot of power. You want to reject the null when the null is wrong and an alternative hypothesis is actually true. And it's very easy to find, truthfully, once we know the type 2 error, because it's really the complement of the type 2 error. So for our example up here, what is the power against my alternative 20.2? The power means the likelihood that I would reject the null when the mean is actually something different from the null and it's at 20.2. And I will do that about 91% of the time. 91% of the time I would reject the null when the alternative of 20.2 is actually true for that school. So we want power high and type 2 low, and they will always be complementary of each other. So once we know how to calculate a power or a type 2 error, then we can always find the other very easily with a little subtraction. Now let's flip over. And I said, how would the answers for the type 2 error and the power change if our sample size had been cut in half? And that's going to impact us because remember, our sampling distribution will change and our standard deviation will change if we actually change the sample size, because our standard deviation of the sampling distribution is the individual over the square root of n. So think about what we're doing. Once again, we're assuming that the mean is 18.6 and alternately it is greater than 18.6. We know now that we're going to use that sample size of only 20 rather than the 40 that we used on the previous page. So if we want to find the probability of a type 2 error, we want to find the probability that we'll accept the null when an alternative is true. So the probability of a type 2 error is when, and against, I should say, 20.2, the mean being 20.2, is the probability that we accept the null. So we are in the acceptance zone when the alternative mean of 20.2 is true. All right, so we have to find the acceptance zone to begin with. So our picture is not going to change dramatically. However, look how our standard deviation does change. So we're putting the 18.6 smack down in the middle. And we know that once we get up here, and we are using a significance level of 0.05. And notice what would happen if I used a significance level of 0.01, 0.1, then this would change this z-value. And so I now need to convert that into an x bar. So I'm still using that same idea that I had before, except now this number is changing to a 20. Okay, so I'm using that conversion factor, and that's how I got this 18 plus, and I'm still using the same z-value, and now this number is changed. And now what do I need to do? I know where my acceptance zone is. Now I have to find the likelihood of the acceptance zone when the alternative is 20.2. New picture. And I'm just affecting the standard error, the standard deviation of the sampling distribution. And so I'm finding what's the likelihood of that region, which is now at a different z-value. Notice how it's changed its position. And so when I convert this number with this new standard deviation of the sampling distribution, look what type of a z-value I get here. I have a 32% chance of making a type 2 error. If I cut my sample size in half, I dramatically increase my chance of having an error. Now, what is my power? My power I can calculate two ways. First of all, I can just subtract. Take the answer I got here, 1 minus that, we'll find that I have a 67 or 68% power. And remember that this is the likelihood, probability that I will reject the null when the mean, get some more lead there, of 20.2 is actually true. And that's the easiest way. Now, if I had to find the power originally without finding the type 2 error first, what I could do is go back up here and know this magic number that we were finding, that x bar, was this 19.85. Well, remember that if less than or equal to 19.85 is my acceptance zone, then the rejection zone would just be greater than 19.85. And so my rejection zone would be this region, and I would be trying to find what's the likelihood of my rejection zone if this alternative mean is true. And so I would be taking this minus this divided by the standard deviation over the square root of n to get this z-value, and I would be finding basically in the picture the opposite end of the curve. So this would be my rejection zone here, and this would be my acceptance zone in here. And so this area we can see is bigger than 50%, and that's actually about 68%. And this area is my likelihood of a type 2 error, and that's the 32% approximately. And I think that's enough for right now, and we'll do some practice.